Hey everyone, this is video number 5 where we explore, discover, and take joy in that most beautiful of mathematical subjects, complex analysis. Our ultimate goal in this video is to get to complex subtraction and its geometric interpretation in terms of vectors, but the majority of this video is going to be spent talking about linear algebra and abstract algebra. Now, don't click away. Linear algebra and abstract algebra are much more interesting than they seem when you get into them more deeply. They are abstract, but the key thing is we're going to try to understand properties of, well, in this case, the complex numbers as a vector space over the real numbers, and it really gets at the core reasons why things are true. It's interesting because we make connections between subjects. That's what leads to understanding. If you like this content, please like, share, and subscribe. I really appreciate it. So what does it mean to relate complex analysis here at the beginning to linear algebra? One thing I have emphasized recently in recent videos is talking about complex numbers as vectors, both in terms of vector addition and scalar multiplication. We can summarize that by saying that the complex numbers, C, this special symbol represents the complex numbers, is a so-called vector space over the real numbers. The complex numbers can be thought of and plotted as vectors, arrows in a plane, where we scale them by the real numbers. That's not the only way to think of the complex numbers as a vector space, but that's the simplest thing to do at first. This actually means lots of things, but let's try to get at some of the basic, most important properties that this means right away. I am usually going to use the Greek letter lambda for my real scalars. This is a real number here. We call it sometimes a scalar because, as we saw in video number 4, we can use it to rescale the complex number. For example, if lambda is 2 and we multiply 2 times a complex number z, if we think of that complex number as an arrow, a vector, multiplying it by 2 rescales it by a factor of 2. It makes it twice as long and in the same direction. If lambda is a negative number, like simplest negative number is -1, it also involves a reflection. -1 times z is an arrow that points in the opposite direction of z and has the same length or modulus as we talked about in video number 4. What does it mean for this to be a vector space? In part, what it means is that when you multiply lambda times a complex number z, you still get another complex number. That's called closure. We can confirm that if we make some assumptions. We make some assumptions, first of all, on what it means to multiply lambda times z. It means we multiply lambda times the real part and we multiply lambda times the imaginary part. So we get lambda times x for the real part of the answer, plus I times lambda times y will be the imaginary part of the answer. Because we know real numbers are closed under multiplication, that means that lambda times x and lambda times y are real numbers. They are elements of the set of real numbers. And we've got a real number plus I times another real number. That is a complex number. This is what it means for this kind of operation to be closed in the complex numbers. This real scalar times this complex number is another complex number. Being a vector space over the real numbers means lots of other things. I don't want to list out all the properties, but let me just mention a few. One property is a distributive property. If we take lambda times the sum of two complex numbers, z1 plus z2, that's the same as lambda times z1 plus lambda times z2. How could you verify that? You could write z1 and z2 in terms of their real and imaginary parts, use the definition of what it means to add complex numbers in terms of their real and imaginary parts, use what we just talked about in terms of what it means to multiply a scalar times a complex number, expand it all out, use the fact that this distributive property works for real numbers, just like we verified that closure works for real numbers. We use that fact, and ultimately verify this property in the end by thinking again about real and imaginary parts. That's a distributive property of scalar multiplication over complex addition. There's another distributive property here as well. You can also take the sum of two real numbers, lambda 1 plus lambda 2, and multiply times a complex number, and you can distribute z through the parentheses. You can get lambda 1 times z plus lambda 2 times z. That's another property that vector spaces have. Another kind of property is called associativity. if we've got lambda 1 times the complex number lambda 2 times z, so the implication here with parentheses is do lambda 2 times z first to get a complex number, and then take that complex number times this real scalar lambda 1, giving you in the end a complex number. That can be obtained by doing lambda 1 times lambda 2 first before multiplying by z. That's called an associative property. These properties are about the relationship between the scalars and the vectors, scalars again being real numbers and the vectors being complex numbers. There are other implications of being a vector space purely related to the complex numbers themselves with respect to addition. You can say the complex numbers is an abelian group under complex number addition. An abelian group under complex number addition. What does that mean? That means lots of things too. There's a closure property. z1 plus z2, if you've got any two complex numbers and you add them according to how we defined addition in terms of real and imaginary parts, when these are complex numbers, that's in C, this is in C, the result is in C. That's a closure property. There's also an associativity. z1 plus z2 plus z3, where I put the parentheses here to emphasize do that addition first before you do this addition, is the same as, well, this is supposed to be a z3 here, by the way, is the same as z1 plus, in parentheses, z2 plus z3. In other words, I can do this addition first before I do that one. And that also ultimately means I don't even have to write the parentheses. It's understood what it means to add three complex numbers. That's an associative property. Being an abelian group, emphasis on the word abelian, also means we have a commutative property. z1 plus z2 is the same as z2 plus z1. Why do these things work? Again, you can go back to the definition of complex number addition in terms of real and imaginary parts. I would encourage you to do it on your own. It's not too hard. Thirdly, there is an additive identity. The complex number 0 plus 0i, which we could just call 0 for short, is the additive identity. If you add that to any given complex number z, you get that complex number z back. Finally, we have also what are called additive inverses. Given any complex number z, there exists, this backwards e is a fun way to mean there exists, another complex number suggestively written as negative z in the complex numbers, such that, st means such that, when you add z and negative z in either order, and it's a commutative group, so we can do this in either order, an abelian group, we get the 0 plus 0i, we get the additive identity. Yes, negative z is suggestively written as our symbol for the additive inverse. It does mean the same thing ultimately, though this takes proof, as negative 1 times z. That's a scalar multiplication, as we talked about in video number 4. But the key thing that we want to get out of this for this video is this allows us to define complex number subtraction abstractly. Okay, now I could have defined complex number subtraction a little less abstractly, you might say, by focusing on real and imaginary parts, and I will do that, but we can think of purely in terms of the abelian group properties, and in particular this last one to define complex number subtraction, and this is going to be helpful for geometric interpretation. If I've got two complex numbers, z1 and z2, what does it mean to subtract them? To do z1 minus z2, in reality it means do z1 plus the additive inverse of z2. Negative z2 means this additive inverse, the thing I need to add to z2 to get the additive identity 0. And yes, that is the same as z1 plus negative 1 times z2. So effectively, I'm defining subtraction using addition. That's actually important in lots of different contexts. I could have defined complex subtraction a little less abstractly. I mean, it's still abstract, but a little less abstractly in terms of not relating it to group theory, by talking in terms of real and imaginary parts. I could have written z1 is x1 plus I times y1, and z2 is x2 plus I times y2, and said, hey, that means z1 minus z2 has a real part equal to the difference of these real parts, x1 minus x2, and an imaginary part equal to the difference of these imaginary parts, y1 minus y2. That would be more analogous to how we define complex number addition. But the benefit of doing it this way, again, is to relate it to abstract algebra and also ultimately to linear algebra. The lambda, when you do subtraction, is -1. Again, there's a reason for this. This is going to allow us to interpret complex number subtraction geometrically in terms of vector addition. And let's do that now with an example. Let's let z be the complex number 4 plus 2i, and let w be the complex number 1 plus 3i, and we want to interpret z minus w geometrically. As far as a calculation goes, do it in terms of real and imaginary parts. 4 minus 1 is 3, 2 minus 3 is -1, so I could write that z minus w is 2 plus -1 times I. More simply, write that as 3 minus I. But how do you interpret this geometrically? We can do it with vectors, and amazingly, we can actually do it in two important ways. Let's draw both z and w here first. Z is 4 plus 2i, so I go to the right 4 and up by 2. There is z as a point. I can also draw its position vector. I can think of the arrow there as being z as well. Right there, w is 1 plus 3i. It's right here as a point. And as a vector, it's right here. Either way to think about w is fine. They both have their benefits. Where should I draw z minus w in this picture? Well, we thought of z minus w as z plus -1 times w. We saw from the last video that when you multiply a complex number by -1 as a vector, it turns it around the opposite direction but the same length. Negative w is going to be right there. And then I can use the parallelogram law that we learned about in video number 4 to geometrically interpret z minus w as z plus -1 times w. I can translate z down here and plot it, being careful to do it right, like that, and translate -w over here and plot it like this. And by the parallelogram law for vector addition, that means the sum z plus -w as a position vector starting at the origin will go from the origin to where these vectors here meet. Right there, that green arrow can be thought of as z minus w. Another way to think of this is that I can translate this vector up here, and I see that it connects the point for w, or the tip of the arrow for w, with the point for z, or the tip or head of the arrow for z. Z minus w is up there as well. That's pretty nice. It's an arrow that goes from the tip of w to the tip of z. Algebraically speaking, it's illustrating, in terms of the head to tail definition of vector addition, why we define z minus w as z plus -1 times w. Because when we add w and z minus w, it should make sense that the w should cancel, leaving us with z, and that's what we've got. The head of z minus w, when you put its tail at the head of w, is pointing at the head of z, illustrating this fact. W plus z minus w is z. Both of these geometric interpretations are valid, and they're both useful. I especially like this one, actually, drawing z minus w as this arrow. That's going to be especially helpful for calculus when we think about interpreting derivatives in complex analysis. And we end with a Mathematica demonstration of complex number subtraction. That's actually this second bit of code here. I do want to emphasize something I forgot to emphasize in video number 4 with this Mathematica code that we saw that allowed us to multiply a complex number by any scalar and interpret it visually. I wanted to emphasize that because of the locator command here, we can also pick our points here and move them around so that we see that we can do this for any complex number in the plane. All right, getting back to complex number subtraction, this bit of Mathematica code here illustrates both the head-to-tail law and the parallelogram law, but now for subtraction in both ways like I just showed you. And so what we got here are two complex numbers, z and w, the ones I plotted by hand here a few minutes ago. I could move these around if I like, I also have negative w plotted in more of a light blue here. I've got z minus w up here, but as with video number 3 where I talked about the geometry of vector addition, we can also use these sliders here to move negative w and z to create a parallelogram to also illustrate where z minus w is down here, like I drew by hand as well. So these two pink vectors are both representing z minus w in the same ways that I showed you by hand. This is how you can do it in Mathematica. And again, the benefit of Mathematica is you can click on these things right here and move these things around and illustrate these ideas for any given complex numbers as vectors that you start with. That's it for this video. I hope you have a good day. Strength and honor to you.